You know how a huge factory seems to know exactly how many parts it needs, or how a power grid can predict a spike in demand right down to the minute? Well, that's not magic. It's all part of this high-stakes quest to see into the future, and it's called time series forecasting. Today, we're going to pull back the curtain on this whole world, from the old-school statistical tools that got us started, all the way to the mind-blowing AI models that are changing, well, pretty much everything. So here's the game plan. We're going to start with why this is such a massive deal. We're talking big money. Then we'll actually decode the data itself. After that, we'll look at the classic tools and then the AI game changers. And of course, how you choose the right tool for the job. And finally, we'll take a little peek at what the future of all this looks like. So let's start with that big money. Why is this a modern-day gold rush? First things first, why is everyone, especially in big industries like manufacturing, so completely obsessed with predicting what's next? Well, as you can probably guess, it all comes down to the numbers. And believe me, the numbers here are absolutely staggering. Just look at this number. By 2033, the market for AI, just in manufacturing, is set to be worth over $156 billion. That's not just some random valuation. That's the financial rocket fuel driving this entire race for the perfect prediction. And you know, that number isn't a flash in the pan. This market is growing at an incredible 45% every single year. So why? It's because companies are pouring billions into this to get ahead of machine breakdowns, to perfect their supply chains, and to slash waste. And they do it all by getting better at seeing what's just around the corner. The raw material for this gold rush, it's data that unfolds over time. So this is the key. We have to understand what we're working with, and that's time series data. The easiest way to think about it is like a heartbeat monitor for a factory, right? It's just a constant stream of information recorded at perfectly regular intervals, every second, every hour, you name it. This data holds all the secret patterns of the past, and that's our only real key to unlocking the future. Okay, so we know what the data is. Now let's actually break it down, because here's the thing. Before you can even think about predicting the future, you have to understand the anatomy of the past. Any time series, and I mean any, no matter how messy and chaotic it looks on a chart, can almost always be broken down into three fundamental pieces. You can think of it kind of like a piece of music. You've got the main melody, you've got a repeating rhythm, and then you've got some random background noise. Let's look at each one. First up, you've got the trend. This is the big picture, the long-term movement. Is your factory's energy use slowly creeping up over the year? Is a certain product's popularity gently fading away? That's the trend. It's that long, slow melody line playing out over time. Next up is seasonality. This is the predictable rhythm of the data. You know, think about ice cream sales going through the roof every single summer, or a factory's power usage spiking every weekday afternoon right before quitting time. These are the repeating cycles that give the data its pulse. And finally, whatever's left over after you account for the trend and the seasons, that's what we call residuals, or, just noise. This is the random, unpredictable static that doesn't seem to fit any pattern. And here's the wild part. This is where the real edge is. Anybody can spot the summer sales rush, but the company that can start to predict even a little bit of this random noise, that's who wins. So, how did we first try to tame this data, this noise? Well, that brings us to the very first generation of forecasting tools, these statistical classics. This timeline here is kind of like our roadmap for the whole history of this field. For decades, forecasters relied on a really trusted set of statistical models. You can see them over here on the left. The classic methods like moving average and, for a long, long time, the star of the show, ARIMA. Let's use an example. Imagine you're trying to predict tomorrow's temperature. An ARIMA model does it in three really smart steps. First, the autoregressive part looks back and says, okay, what was the temperature the last few days? It's looking for a basic pattern. Then, the integrated part is smart. It knows it's summer, so it accounts for that overall warming trend, which makes the data way easier to work with. And finally, the moving average part looks at yesterday's forecast and it says, I was off by 2 degrees. Then it actually uses that mistake to make today's prediction even better. Pretty clever, right? For a long, long time, this was absolutely state-of-the-art. But ARIMA and its cousins all have a kind of Achilles heel. They really love clean, simple, linear patterns. So what happens when the real world is messy and complex and it just doesn't move in a straight line? And this is where our story just takes a massive turn. This is the moment when we stopped trying to apply rigid formulas to the data and started teaching machines to find the patterns all by themselves. Welcome to the age of AI. It all starts with something called an artificial neural network, or ANN. I mean, just think of it like a digital brain that you can actually train. You feed it tons and tons of historical data, and it just goes to work, tweaking the connections between its neurons, trying to find all those complicated, hidden relationships that a human would never, ever spot. And then, out the other side comes a forecast. But the real game changer for time series data was a special kind of neural network, the recurrent neural network, or RNN. And the difference is one crucial word: memory. A standard network looks at each data point like it's the first time it's ever seen it. But an RNN has these feedback loops which let it remember what came before. It's like, to understand a sentence, you have to remember the words that came earlier. That ability to understand sequences is what makes RNN so incredibly powerful for forecasting. And that idea just keeps evolving into even more powerful models, like this one, the encoder-decoder. Think of this thing as a universal translator for time. The encoder part reads a whole chunk of past data, like, say, the last week's worth of sensor readings, and it squishes it down into a single, compact thought. Then, the decoder takes that thought and translates it into a whole sequence of future predictions, like what the next 24 hours are going to look like. It's a total game changer, especially for long-range forecasts. Okay, so we've got the classic, reliable statistical models on one hand, and these super powerful AI game changers on the other. And that creates a brand new problem, right? With all these amazing options, how in the world do you choose the right one for your specific problem? This table really just gets right to the heart of it. There is no single best model. It all depends. Look at the top. Let's say you're forecasting something steady and predictable, like a grocery store's weekly demand for milk. A classic model like ARIMA is perfect. It's fast, it's simple to understand. But what if you're trying to predict something chaotic, like a stock price or the energy output of a wind farm? That's where you need the heavy-duty power of an ANN or an LSTM. They can handle those wild, nonlinear patterns. And as we go down, you see other specialized tools, like Profit, which is amazing if your data has strong weekly or holiday cycles. Or SVMs, which are great when your data is super complex and it's easy to get fooled by the noise. The big takeaway is that you have to match the tool to the specific challenge you're facing. So that brings us to our final stop on this journey. We've gone from simple averages all the way to digital brains. So the big question is, where does this whole quest to predict the future go from here? The future is looking pretty incredible. The next wave is all about making these models even smarter. We're talking about explainable AI, which will finally let us peek inside the black box and understand why a model is making its predictions. We're building hybrid super teams that combine the stability of the classics with the raw power of AI. We're even developing systems that can learn from one forecasting job and apply that knowledge to a totally new one. And maybe the coolest of all, models that can learn and adapt their forecasts in real time as new data is streaming in. This whole quest is pushing us towards a future where we can be more efficient and prepared than ever before. But it does leave us with one final, and I think really important question to chew on. As our predictions get closer and closer to perfect, will our biggest challenge be dealing with the future we can see coming, or will it be the one that we never even thought to look for?